Okay, so for section 5.3, title this Solving Trigonometric Equations. And so to get you warmed up for this section and what you're going to be doing, I have two problems for you to try. So go ahead and pause the video and try each of these on your own. The directions say solve for x given 0 is less than or equal to x is less than 2 pi. So we want an angle whose sine, when you multiply it by 2, gives you 1. So we'll start by isolating the trig function sine. We'll divide both sides by 2. And so when we do this, we end up with sine of x equals 1/2. And so our reference angle for this one is going to be 30 degrees. So we have 30 degrees as one of the answers for the value of x. And then also the second quadrant will produce your other one, so that'll be 150 degrees. Since this says between 0 and 2 pi, I'm going to go ahead and put this in radians for both of these. So that's going to be pi over 6 and 5 pi over 6. And these would be what you submit as your two answers. For number 2, it takes a little bit more work. You'll notice you have a trig function on the left and one on the right, so you'll put them on the same side together. When I do that, I'll get 2 sine of x, because I'll add sine of x to both sides. And then I'll also add square root of 2 to both sides at the same time. Then I'll divide both sides by 2. So sine of x equals root 2 over 2. And so the reference angle for this one is going to be 45 degrees. So one of my answers will be 45. Again, the second will be in the second quadrant. That'll give me 135. And since it wasn't in radians, that'll give me pi over 4 and 3 pi over 4. So this will be the type of thing we're going to be doing in section 5.3. When we were working in the other sections for 5.1, 5.2, 5.4, and 5.5, we were proving identities, which means with identities, you can put in whatever x's you want. There's infinitely many answers. It's actually all solutions. However, now we're going to be solving equations that are only true for specific values of x. You don't have to write any of this down. This is just a quick review from your earlier chapter 4. And so in this section, because we're going to be solving for theta, we have to remember how to put our angles in each of the different quadrants. And we also need to know the signs of each of these as well. Your reference angles for the first quadrant are going to be necessary, knowing their sines, cosines, and tangents also. So let's go ahead and begin. Go ahead and pause the video and write this problem down. To solve this, we want to again isolate the trig function, so we'll add 2 to both sides and then divide by square root of 3. Since cosecant has a reciprocal of sine, I'm going to go ahead and flip this and work with sine of theta equals square root of 3 over 2 instead. And so that reference angle is going to be 60 degrees. And then the other one is going to be in the second quadrant for 120 degrees. So my answers will be pi over 3 and 2 pi over 3. You'll notice in the directions, however, it says to give the general solution. What that means is that you are going to give a formula for all of the answers. If you compare this to the directions in the warm-up, it only wanted answers between 0 and 2 pi, which was 1 revolution of the unit circle. However, there's technically infinitely many answers. So for my 60 degrees, my first one, which is the same thing as 2 pi over 3, my next answer after this one that would make this a statement true is to add a full 360 degrees to 60, which would be 420 degrees. That would be my next answer. Or I could add 2 pi to 2 pi over 3, making that 8 pi over 3. So one of my general solutions then would be to take pi over 3 and add 2 pi. But because I could do that again another time and add another 2 pi to now 8 pi over 3, you would also be able to do this infinitely many times, which means you would add infinitely many multiples of 2 pi. So I'm going to multiply that by n, and I'm just going to simply state that n is a part of your integers. So you would make your z with the double stem on it, or you can just simply write out that n is equal to -1 with a dot 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 to the left, 0, 1, and then a dot 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 to the right. That would be sufficient as well. You would do the exact same thing for 2 pi over 3, so the same idea holds. You could add infinitely many revolutions to 2 pi over 3, and so you would get your other general solution of 2 pi over 3 plus 2 pi n as well would work for the second set of answers. You've already written that n is an integer, so you only have to write it down one time. This would be what you would submit if I asked you for the general solution. This is a graph of sine of x, and so as you can see, the y value, sine of x is square root of 3 over 2, is around 0.8-ish. So on the graph of sine, this is what's showing you that you do truly have infinite many answers, and each of these answers are 2 pi or 360 degrees apart from each other. And so those would be the solutions here that you would give. Here's the next example. We're still finding the general solution, so we want to get sine by itself. We'll take the square root of both sides. You'll put your square root at both the top and the bottom. Don't forget that plus or minus since sine is being squared. We'll multiply by the square root of 2 both top and bottom in order to rationalize. And so now we have an angle that we need to find whose sine is square root of 2 over 2, but it also needs to be negative square root of 2 over 2 as well. The reference angle for this is going to be 45 degrees. And so it's going to end up being all 4 of them in the unit circle, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now, this is again only if you have one revolution of the circle. And because it wants the general solution, you need to give them all of the answers no matter how many times you go around the circle. So we could do this the exact same way we did the last one. We could take pi over 4 and add 2 pi in just like we did before. But you'll notice that we have some extra answers that we didn't have before, 2 of which actually are diagonal from each other on a straight line. So here is 5 pi over 4, and here is pi over 4. So in order to get from one to the next, I don't have to make a whole nother revolution to get to my next answer. Technically, to get from pi over 4 to 5 pi over 4, I only need to make half of a revolution of a circle. So if I take pi over 4 and just simply add pi units to it now, I would get my next answer. Then if I take, this would be 5 pi over 4 here. If I add pi to that, that would give me the same thing as taking pi over 4 and adding 2 pi units to it. So I don't have to write 4 different instances of the general solution. I can get rid of this one and just simply write pi over 4 plus pi n, because that will cover the 5 pi over 4 and then everything in between those two by just simply going pi units apart from each of my answers. I could do the exact same thing with 3 pi over 4 and just simply add pi n to that as well, because that is also diagonal from 7 pi over 4. So to get from 3 pi over 4 to 7 pi over 4, I just simply need to add pi units. And then to get from 7 pi over 4 to the next answer, which would land on 3 pi over 4, again, I would just need to add another pi units. So the idea holds here as well. And so you just simply need to write n as an element of the integers one time, and then there is your general solution. This is what you would submit as your general solution. Now, if I were to do that, try to do that same thing, or I would not be able to do that same thing on this one, because on number 1, because when we did this, pi over 3 and 2 pi over 3 were not diagonal of each other on a straight line, so in this case I did have to write 2 of the answers, or both of the answers as 2 separate answers, and so I had no choice but to write these individually. These answers, however, I have 4 of them, but I don't need to write 4 of them. 2 is sufficient. Okay, here's your next example. This is similar to your warm-up. So if you'd like to try it yourself, you can go ahead and pause the video. You'll notice this time that it does give us a restriction for theta. It tells us we only need to go 1 revolution around the circle. So we're going to take our cosines and put them on the same side. So I'll subtract 2 cosine theta from both sides. I'll subtract 3 at the same time. So now I have 2 cosine theta equals -1. We'll divide both sides by 2. And so I need an angle in the second and third quadrants, because cosine is negative there. That's going to give me a cosine of -1/2. My reference angle for that is pi over 3, or 60 degrees. So in the second quadrant, that's going to be 2 pi over 3, and in the third, it'll be 4 pi over 3. These are my 2 answers, so I'm done. Now, when doing these different things for solving trig equations, you have some steps that you can take So one of the things that you want to do, if there are multiple trig functions, we'll see an example of this in just a moment, we want to make sure that all of our trig functions are the exact same one. You don't want to have both a sine and a cosine in the problem. Try to get them to one trig function if you can. If there are places you can use your identities, go ahead and do so. You may need to substitute some stuff out, but that doesn't mean you have to every single time. It's not always necessary to substitute your identities. You want to work on trying to getting one side equal to 0 when possible. Therefore, you can take your GCF and then use your zero product property to solve for your trig functions. There are times that you have your equations in quadratic form, so you may be able to reverse FOIL and solve that way. If you see any angles with 2 pi in it or theta over 2 in it, then you're going to want to use your double angle identities or your half angle identities. So it's just plain theta. Oh, that was number 6. I'm sorry, I skipped number 5. We'll see examples of number 5 where you have multiples of theta, like for example, solving something like sine of 3 theta equals 1/2. This has a special thing that we have to work with, and it has something to do with adding 2 pi and subtracting 2 pi. We'll talk about that when we get to that kind of example. All right, so let's start to make our problems a little bit harder. Here's your next example. In this one, the technique that we're going to use, because they both have a sign in common, we're going to go ahead and take out a GCF of sine. When we do that, it looks like this. We'll now use the zero product property and set each of those equal to 0. In the first example, sine of theta is equal to 0 whenever theta is 0 and pi. We would use the answer of 2 pi as well, but because there's no equal to symbol here on the 2 pi, we're not going to do so, so 0 and pi is sufficient. And then for the second one, sine of theta equal to -1/2. The reference angle is pi over 6, but we want it to be in the third and fourth quadrants, so our two answers are 7 pi over 6 and 11 pi over 6. And this problem is now done. You can pause the video and try this one yourself. I'm going to go ahead and move on from it since the answer is here. For your next example, this is a function of the quadratic form. If you're not sure how to solve something like this, you might want to start by replacing that sign with s instead. And once you do that, it may be a little bit easier for you to factor it. So when we factor this, we're going to get a 2s and a 3s. We're going to get a 1 and a 1. We'll make this one a positive and this one a negative, and then we'll end up putting those s's, replacing those s's back with sign. So you get 2s plus 1 and 3s minus 1. However, that wasn't really s, so we're going to put those back, and so we have that we're going to solve for sine of theta equals 1/3 and sine of theta equal to -1/2. For the first one, you need a calculator. That wouldn't be something I'd expect you to know because it's not one of our unit circle values. So in your calculator, you're going to plug it in, and you'll do the inverse sine of both sides. And one of your answers will be 19.47 degrees. But keep in mind, you're going from 0 to 360 degrees, which means you have a second answer. That second answer is going to be in the second quadrant. Since this line to the left, the negative x-axis is 180 degrees, and if you flip 19.47 across the y-axis, it'll be 19.47 degrees away from 180. So you'll take 180 and subtract 19.47, and that'll give you your second answer of 160.5 degrees approximately. And then the sine of x equal to -1/2, we just solved these on the last example. The reference angle is 30 degrees, so we'll subtract that from 360 and add that to 180 to get 210 and 330 as my answers for this one. Go ahead and take a moment, pause the video, and try this example. I'm going to go ahead and move on since you have the answers for it. And I'm going to go ahead and stop the video here because I won't have time within the video to do this one, so I'm going to go ahead and pause it now and start a new video.